Hi everyone. Today what we're going to talk about are double replacement reactions, and in particular, we're going to talk about precipitation reactions. So let's remember what a double replacement reaction is. In a double replacement reaction, we're going to have a compound AB. When you have a compound AB, what you want to notice is that A will be the cation and positively charged, and B will be an anion or negatively charged. This could be something like sodium chloride. This could be something like sodium nitrate. Remember that nitrate altogether is one ion, and it's going to stay together as a unit. So we're not going to break up the nitrogen and the oxygen. We're going to leave the nitrate. If you had something like sodium sulfate, the A would be sodium and the B would be sulfate. So they can be various things, but A is always representing the positive cation and B is always representing the negative anion. We're going to react it with another compound that is also having a positive and a negative. And what's going to happen is the positive A is going to end up going, oops, sorry, that should be a D. Let me fix that. That should be a D. A is going to go with D, and we're not going to write B first because B is negative. Whenever you're writing a formula, always put the cation first. So I'm going to put CB so that I also have my positive and my negative. Now, the type of reaction that we're going to talk about in this particular clip are precipitation reactions. Precipitation reactions are reactions that form a precipitate. A precipitate is a solid that forms from the mixing of aqueous solutions. So I know we haven't really formally talked about solutions. So what I thought I'd do is tell you a little bit about solutions before we go into mixing them together. So if we're talking about a solution, all that really means is that we have a homogeneous mixture. Remember, homogeneous means it will be, the components will be evenly dispersed throughout the entire mixture. And we have two words with solutions that you should also be aware of. One is solvent and one is solute. All solutions have a solvent and at least one solute. Solvent is the component that's present in the highest amount and the greatest quantity. And the solute is the component or components present in lesser quantity. This is generally true unless one of the components is water. If one of the components is water, water is always taken to be the solvent regardless of how much is present. So even when you have something like rubbing alcohol is typically 70% isopropyl alcohol, which means that it is only 30% water. However, water will still be considered to be the solvent. So whenever water is one of the components present, it will be the solvent. So what I need you to understand is how do things dissolve into water and what things will dissolve and what things will not dissolve before we move on. So I'm hoping to share a clip with you about what things are soluble and then a video of how things dissolve so that you can get an idea of how we're going to work through these problems. So for a second, let me just show you the solubility table. And so this is our solubility table. And if you look at the solubility table, they're shown in different ways. The one in your textbook's very similar to this. It has the same information. When you look at this, what it's telling you is these things on the top are things that are soluble ionic compounds, and the one on the bottom are insoluble. So notice that there are no exceptions here when you go across. All nitrates are soluble. When you come down here to the bromides, you're going to see that bromides are soluble unless they're silver, mercury, or lead. And then if you come down to these, this is the bottom one are telling you all sulfides are insoluble, except for ones with ammonium, alkali metals. And remember, alkali metals are metals in group 1. calcium, strontium, and barium. You don't need to memorize this table. You will always be given this table. So what I would suggest you do for the rest of this, if you have the ability to print it out, print it out. If you can't print it, what I would do is go to Canvas and open this up. It's posted for you in the module. Open it up, and so you can click back and forth and refer to it, because we're going to need it a lot throughout the thing, throughout this lecture. The other thing I want to show you is how things actually dissolve. So I want to show you this quick little video clip. It's only 53 seconds, so watch this and then we'll talk about it.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
So what that clip is basically saying is when we have NaCl solid,
sodium chloride to water. Okay?
Whoops. Sorry, I think I'm back now. I think I'm back now. So what this is saying is the sodium chloride, when you have it as a solid, it's just that, as you would see, white crystalline powder. But when you say NaCl aqueous, what you really have is sodium chloride dissolved in water. And so what that would mean is if you had a glass of water, you're going to have the sodium ions that are going to be surrounded by water. I can't draw them all in there. And you'd have chloride ions also surrounded by water. What's important to note is that when you have this, the sodium ions and the chloride ions are not really attached to each other anymore. When you write sodium chloride aqueous, what you really have is sodium ions surrounded by water and chloride ions surrounded by water. The sodium and the chloride dissociate from one another. And so this is going to be important, and I'll show you how as we go through a few examples. So let's actually just do some examples of precipitation reactions. So let's start out with ones that are 1-to-1. So if I told you we started with silver nitrate, aqueous, and sodium chloride, aqueous, what would we get for products, and how will you know what the products are? Well, first of all, let's look at what we would have it floating around in the solution if we had silver nitrate. If we had silver nitrate, what we'd basically have is silver ions floating around, and we'd have nitrate ions floating around. So in silver nitrate, that's a 3. In silver nitrate, we'd have silver and nitrate ions floating around. And when we have sodium chloride aqueous, what that would mean is we have sodium ions floating around, and we have chloride ions. So these would be our reactants. Now, if a reaction is going to happen, they're going to switch partners. When I mix sodium chloride into silver nitrate, all 4 of these ions would originally be floating around. What would be my other combination? Well, if I take the positive silver and I mix them with the negative chloride, I would get AgCl. It's just going to be 1-to-1 because silver is +1 and chloride is -1. Now, if I go back and I look at my solubility table, it will show me that chlorides are typically soluble unless chloride's soluble except, among other things, silver ions. So if they're not soluble with silver ions, that's going to tell me that this will be a solid. That means it's not going to be floating around anymore as silver ions and chloride ions. It's going to be AgCl stuck together as a solid sticking at the bottom of the container. What's my other possible container, my other possible compound? Well, my sodium can mix with my nitrate. And again, sodium is +1 and nitrate is -1, so it's just going to be NaNO3. Now this is going to stay aqueous because if I look on my solubility table, it tells me that all alkali metals are soluble and all nitrates are soluble. So that means that NaNO3 is always soluble. So I'm going to write it as aqueous. So what does that really mean? It means I still have sodium ions floating around because it's aqueous, and I still have nitrate ions floating around, aqueous. So this would be my overall reaction right here. So in the chemical reactions lab, that was the only reaction that was asked of you to write. That's the overall reaction. But let me give you a couple other terms and let's look at this in a little bit more detail. So again, this is my overall reaction. Silver nitrate, aqueous, plus sodium chloride, aqueous, is now we know going to turn into silver chloride solid and sodium nitrate aqueous. So this is my overall reaction. From this, I can write a total ionic equation. My total ionic equation, I'm going to show all the ions, everything present to begin with and ending. So this is where I'm going to show that I would have had silver ions plus nitrate ions plus sodium ions plus chloride ions to begin with. What am I going to have when I'm all done? The silver and the chloride are no longer going to be ions floating around in the solution because they're going to join together and form a solid, the precipitate. But I'm still going to have sodium ions floating around, and I'm still going to have nitrate ions floating around. So this is my total ionic equation. It's showing me everything I have to start with and everything that I have to end up with. Now, if you notice what's true on here is that I have nitrate ions and I have nitrate ions. Nothing really happened there. And I have sodium ions and I still have sodium ions. So if I want to show what's really called my net ionic equation, this is going to show only things that have changed. So silver started out as an aqueous ion and chloride started out as an aqueous ion, but they end up being a solid. So my net ionic equation is really just that silver ions and chloride ions combine to give me a solid. What happened to the sodium and the nitrate ions? They were there in the beginning and they were there at the end. Those are referred to as spectator ions. These are ions that undergo no change. So spectator ions are left out in the net ionic equation, but they're shown in the total ionic equation. This is quite a lot of work to do, so I thought I'd do is go through at least 2 more examples with you, and then this is something that if you can join one of the live streaming workshops, which we'll start doing on Monday at class time at noon, then you'll be able to go through a few more examples live and ask questions. So let's try another one. So this one's a little bit similar so that we don't make too many changes at once, but I'm now going to start out with silver nitrate, and instead of reacting it with sodium chloride, we're going to react it with magnesium chloride. Whoops. And now if we just want to find our overall reaction, you can just use the rules and knowing the charges of the ions. So remember now silver is going to be A, nitrate's going to be B, magnesium's going to be C, and chloride's going to be D. So when I'm all done over here, I want to write AD plus CB. So I'm going to take silver and I'm going to react it with chloride or combine it with chloride. Silver is +1 and chloride is -1, so I can just write my formula as AgCl. CB, C is magnesium Magnesium is +2. How do I know that? It's in group 2, but it's also got 2 chlorides. And then I have nitrate, 1-. So I can't just write MgNO3. If I write MgNO3, that's not a neutral compound because magnesium is +2 and nitrate is -1. I need 2 of these so that my total negative -2 is the same as my total positive +2. So to write this, I need to say 2. That is the very first step in solving any of these reactions. Now, if you notice, I wrote parentheses, but I didn't write anything into them. So in these parentheses, you now have to decide whether the substance is soluble or insoluble. So step 1, determine the products. Using the charges of the individual ions present. Step number 2 is going to be to determine the solubility of each product. How do we do that? We use the solubility table. That's why I said if you have the solubility table out so you can refer back and forth to it, that would be very helpful. So again, silver chloride, we already did the last time, we know is insoluble. So I'm going to write that it's a solid. Magnesium nitrate is going to be soluble. So I'm going to write it as AQ. So that is the very first thing you need to do in getting your overall reaction done. Now, if I asked you in addition to write a total ionic and net ionic equation, how would they look? So again, here's our overall reaction. We're going to get silver chloride solid, we just determined, and magnesium chloride aqueous. So now if I want to write my total ionic equation, I'm going to write all the ions out. I'm going to show silver ions, aqueous, nitrate ions, aqueous, magnesium ions, aqueous, and chloride ions, aqueous. What am I going to end up with? Silver chloride solid plus magnesium aqueous plus chloride aqueous. Now, hopefully you noticed that, oh, I did something wrong here, didn't I? I should have had nobody, I don't have you in class to show my mistakes here. So what did I do wrong? I don't end up with magnesium chloride. Let's erase that. I end up with magnesium nitrate. Oops, that's very messy. I end up with magnesium nitrate. Oops, that makes more sense. And so when I am over here, I have to erase this as well. We all make mistakes. So I end up over here with nitrate. Now, if you notice, something's not right with this because when I write my final product, I have 2 nitrates, but over here I only have 1. So one thing we didn't go back and do is balance our equation. So balancing equations is not a step to be left out. So if we wanted to balance this equation, I'd need to have nitrates. I have 2 over here, so I need 2 silver nitrates, and then I have 2 silvers, so I'm going to need a 2 here. Now I have 2 silvers, 2 silvers, 2 nitrates, 2 nitrates, 1 magnesium, 2 chlorines, 2 chlorines. Now we're balanced. So if I go back over to here, I don't really have 1 chloride, I have 2 chlorides. And when I get over to here, I don't really want 1 nitrate, I need 2 nitrates. So I'm going to need 2, and I'm going to need 2, and I'm going to need 2. So if you don't balance right away, it makes it a little tricky, but you can catch it when you go to the next step. To get to my net ionic equation, what I'm going to do is get rid of all the spectator ions. What things have changed and what things have not changed. So right now I have 2 silver ions reacting with 2 chloride ions. And I'm going to get out of that 2 silver chlorides. Now, because everything here is 2 to 2, they're going to actually leave them out and just write Ag plus Cl goes to AgCl solid. If you left the 2's in there, I would not mark you wrong right now. I'd just cross them out. But just to know, people aren't going to leave it. If everything's a 2, they're going to give you the lowest whole number ratio. What would be my spectator ions? My spectator ions are the things that have not changed. Ions that do not change. And so what hasn't changed? Changed in status or in solubility, let's say. So what hasn't changed? I have 2 nitrates here and I have 2 nitrates here. So those are my spectators. I have a magnesium here and I have a magnesium here. That is a spectator. So getting rid of the spectators brings me back to 2 silver plus 2 chloride gives me 2 silver chloride, which is my net ionic equation. So I know this is a lot of information and it's probably even more challenging to just watch on the whiteboard. So let's do one more just so that we have it done. And then there's a bunch of practice problems posted on Canvas for you, a worksheet of these that shows all the answers as well. So let's try one more. And I know this is a lot. I'm not trying to minimize this. So let's try something that's not silver nitrate. Let's look at this one. If I have sodium sulfate, aqueous, and I want to react it with barium chloride, aqueous, what am I going to get? So let's try to do the whole thing. So what am I asking you to do? I'm asking you to, 1, write the overall chemical reaction. 2, write the total ionic equation. And 3, write the net ionic equation. Okay, so what steps do we have to do? 1, mix the partners. So we're going to have sodium ions, right? Na1+ ions. We're going to have sulfate ions. This is where you got to remember charges. Sulfate is 2. How do I know sulfate's 2-? Well, each sodium is 1, and I have 2 of them. So I have sodium ions, I have sulfate ions, I have barium. Barium's in group 2, so it's going to be +2. You have chlorides, those are going to be 1- because they're in group 17. I didn't balance this. I just wrote the identity of the ions right now. If I wanted to write down how many of them all I have, sodium I have 2, so I would write a 2 here. Sulfates I just have 1, barium I just have 1, chlorides I have 2. Now, what am I going to do when I mix them together? The positive sodium is going to go with the negative chloride. Now, I'm not going to write it as Na2Cl2. It's just going to be NaCl. Na is 1+, Cl is 1-. I just need 1 to 1. If I look on my solubility table, sodium chloride is soluble. You need to look on the solubility table if you're unsure. What else will I get? Well, the other thing I'm going to get is bariums are going to go with sulfates. Barium is +2, sulfate is -2, so I'm just going to write BaSO4. I need to look on my solubility table and see if that is soluble. Turns out it is insoluble, so I'm going to write that as a solid. Now I need to balance my equation. To balance my equation, I have 2 sodiums, but over here only 1, so I'm going to put a 2 in front. I have 2 chlorides and I have 2 chlorides. I have 1 barium, 1 barium. I have 1 sulfate, 1 sulfate. Everything's balanced. What products will I get? Well, my sodium chloride is still aqueous, so I'm still going to have 2 sodium ions, and I'm still going to have 2 chloride ions. My barium sulfate, I'm going to write as a solid. What I essentially just wrote out is my total ionic equation. It shows all of the ions present. And if I just get rid of some of the messiness that I put on here and I erase these things, you can see that this is now my overall chemical total ionic equation. It shows everything. If I wanted to write the third thing, right in my net ionic equation, what would I do? I want to remove the spectator ions. To remove the spectator ions, just look at what things we have on both sides the same. So I have NaC, 2 sodium ions on this side, and I have 2 chloride ions on both sides. Those are my spectator ions, so I'm going to remove them to write my net ionic equation. And you can leave it in this order, but typically people always put the positive thing first. I don't really care right now. I'm really concerned that you can get the idea. So I'm going to take sulfate ions and barium ions that started out aqueous, and I'm going to turn them into solid barium sulfate. That would be my net ionic equation. So these are a lot, and you got to know the ions, their charges, how they're going to form the compounds. You have to look up on the solubility tables. You have to use a lot of information in order to solve these. We'll finish with one more, and then after this, we'll do some in the workshop together online, and I'll record those so that you can see the questions people are asking. So what if I were to ask you this question, or to solve this problem, and we were to take sodium chloride aqueous and react it with magnesium bromide aqueous? What would we get as products? Well, we could start by writing out the molecular total ionic equation showing all of the individual ions. So I'd have sodium, and I'd have chloride ions, and I'd have magnesium, and I'd have 2 bromide ions. How do I know I'd have 2? Because there's 2 here. So those are the things I'm starting with. If I mix the partners up, what am I going to do? I'm going to mix sodium with bromide. So I'm going to end up with NaBr. I'm going to mix magnesium with chloride. So magnesium is +2 and chlorine is only -1. So I'm going to need to write MgCl2. Now that's going to make me have to go back and balance the equation because I don't have enough. So I'm really going to need 2 of these, 2 of these, 2 of those. Now I have to look at my solubility table. And if I wanted to balance, I'd need a 2 in front of NaBr. Now I'm going to look at my solubility table and decide, are these things soluble or insoluble? If you look up for NaBr, it is soluble. So I'm going to write AQ. And if I look up MgCl2, it is also soluble. So I'm going to write AQ. So what am I going to end up with then on this side? I'm going to have 2 sodium ions, 2 bromide ions, a magnesium ion, and 2 chloride ions. Well, now if I go to get my net ionic equation, remember, remove spectators. What's true is I have 2 sodiums on both sides. I have 2 chlorides on both sides. I have a magnesium on both sides, and I have 2 bromides on both sides. What happens? Everything cancels. Why does everything cancel? Because technically nothing has changed. And so even though I mixed these 2 solutions together, nothing's changed from what I originally had to what I finally have. So what's really true is that I have no reaction. So if this is aqueous and this is aqueous, this is all really wrong. And what I want to say is mixing these together will give me no reaction because the net ionic equation doesn't exist. Everything is canceled out. There is no net ionic equation. So there are some mixed in with the problems that you're going to find this, that there are no products. Nothing has changed. So try the ones that are on the handout posted on Canvas. There are, if you scroll down, there's the problems. It asks you to do the total ionic, the net ionic, predict the products, and the answers are written out. If you're having trouble with those, we can try to go over a few in the live streaming sessions. Till next time.